Okay, so last time we were talking about fluid convection. So we'd seen a movie of what it looks like, and we set up the system as shown here on the left. So we have a plate heated below and cold at the top. A space of which is a planar geometry with a gravitational field, and we figured out that the fluids move when the heat is the heat gradient is strong enough because of buoyancy. And what we had understood was that buoyancy enables the fluid to become lighter, so it then rises. But opposing that is the friction, so that's the shear viscosity eta, but also the thermal conductivity, which will, if you have a local hotspot, will rapidly diffuse away the heat, and so therefore that will reduce the hotspot and therefore reduce the tendency for the fluid to rise. So what we want to do now is we want to formulate this mathematically, and we want to then try to explain why it is that when we look at the system, we see that it self-organizes into these patterns, even in a steady state, and we want to try to understand how that happens. So the mathematical strategy that we're going to use, and all of this, by the way, this is in my notes, ESM, chapter 7, and these are various subsections of that chapter. So what we're going to do is we're going to build a mathematical model using symmetry and conservation laws. And another thing which I'm going to call constitutive relations. What is a constitutive relation? A constitutive relation is something that is specific to the particular material. So this is something specific to the material. So as an example, let me mention Ohm's law, which in elementary physics is just V equals IR. So this is, of course, an approximation. In fact, this is a sort of linear approximation to the response of a system to a potential difference. And the constitutive relation relates the voltage, the current, and therefore introduces the resistivity, or its inverse, the conductivity. So you've all seen those things before. If you were to write down Ohm's law in a more sophisticated way, you would say J is equal to sigma times the electric field. J is a current, sigma is the conductivity, and then you would say, well, there are higher order terms here which are higher order in the electric field, and we just focus on the linear response, and so we just focus on this part here, and that's the linear response. So the way we're going to build this is we're going to try to model now all the ingredients of convection. So the first part of our model is the equation of state. So our equation of state for the fluid tells you, in this particular case, how the density of the fluid depends on temperature. And so what we're going to assume is that we can write that as some reference density rho bar, and then it's going to be something that depends on the coefficient of thermal expansion, and then T minus the reference temperature. So this is going to be our approximation for that, and this is the this thing over here is the coefficient of thermal expansion. So as the temperature goes up, the density goes down. Okay, so that's simple. So now let's write down conservation law. So the conservation law here is mass conservation. And so how do we express mass conservation? Well, that tells you that the density d rho by dt plus the divergence of a mass current is equal to 0. And the mass current is then just given by the density times the fluid velocity. So that's just given by that formula like so. And what we're going to generally assume is that the fluid is incompressible. If the fluid is incompressible, then you can then show from these equations that that simply means that div u is equal to 0. So that would be what we would have if we had an incompressible fluid, and whether or not we have that here depends on the situation. Then the other conservation law that we have is momentum conservation. So why do we need momentum conservation? Well, we don't really have exact momentum conservation, but we have something close to that. We need an equation for the fluid velocity u. The fluid is moving with some velocity u as a function of space and time. And the way we're going to write down that conservation law is we're just going to say that the acceleration is equal to the force divided by the mass. That's the usual Newton's law. So we're going to apply that to a little fluid parcel. So what that's going to end up with is we're going to apply this to a small volume of fluid. And the equation we're going to end up with is this. So we're going to end up is m times acceleration is equal to the force. So if we're looking at a small volume, then the mass is just the density times the volume. So it's going to be rho times the acceleration, which is du by dt. And then that is going to equal the force, which is the force per unit area. So that's going to be minus gradient of the pressure. And then there's going to be gravitational potential, so that's rho times g, and then there's a final term which is which violates momentum conservation, which is the viscosity, which I'm going to write as eta del squared u. So I'll explain these terms in a minute. So this is Newton's equation. So this is acceleration times mass. And then this is equal to the forces. And this is pressure gravity, and over here, viscosity. Okay, so that's the equation. That's not quite correct. We have another term that comes in here, and that term is this one, u grad u. And this term is known as the advective term. And this has a nonlinearity in it. So it's nonlinear because you have this and you have this. So this nonlinearity is what makes all fluid mechanics complicated. Fluid mechanics is complicated because of this nonlinearity. So notice that this nonlinearity comes from here. And so this basically describes inertia. So let me explain to you where this term comes from. So how many people know where this term comes from?
Quick question.
Yes.
Why does incompressible need the divergence?
Okay. So if it is incompressible, then the density cannot change. So then put that into the above equation and differentiate, and that's what you'll get. Okay. All right. So let's just talk about this term. So half the class knows where this comes from. So let's take a side tour and describe where this comes from. So let's suppose I have a scalar quantity, which is a function of space. And let's suppose that this is being transported by the fluid. Okay. So what's going to happen is that the rate at which this quantity changes. So what is this going to be? It's going to be df by dt plus how does the velocity change? Well, remember that the velocity itself is equal to du by dt. So it's going to be df by dt plus df by dx, which is grad, times dx by dt, like so. And therefore that is equal to d by dt plus u dot grad acting on the scalar quantity f. If you've got a quantity that is being advected through a fluid, then its time derivative is equal to this combination over here. So let's suppose that the f itself is a component of the velocity. Then you get the equation that I wrote on the previous screen. So that's where this comes from. Now we're going to use this equation again, not just to see how the velocity field advects, but also how temperature advects. So this applies to any quantity that is being transported by the fluid. So that's the equation of motion. Now let's make a comment about the viscosity. So we defined what the shear viscosity is a couple of lectures ago. So we talked about how we measure it. So why does it come into the equation in this way? So what the shear viscosity tells you is it tells you how it tells you about the forces in a fluid due to differential velocity. Okay? This then is a term that must depend on gradients of u. But it also needs to be translationally invariant and rotationally invariant. So it needs to be translational and rotationally invariant. And so that means that the only term that we can construct that is related to derivatives that is rotationally and translationally invariant, it has to be of the form del squared u. There could be higher order terms, but this is the lowest order term that is linear in u. And so this is this is the lowest order term that we would expect, and the coefficient that goes in here is the shear viscosity. So this is the phenomenological derivation of the equation on the left. This equation on the left is called the Navier-Stokes equation, and we've just derived that in 5 seconds. Well, 10 seconds because I explained it slowly to you. Okay, yeah. So there is a much more convincing. How many people are convinced by this derivation? Well, some of you are. Yeah, most of you are. Most of you know to be convinced. Suppose I derived it by a different way. Suppose I said, we know what a fluid is. Okay, a fluid is a bunch of particles bouncing around in a box. So here's another derivation that I can do. So here is my system. It's a bunch of particles bouncing around in a box. That's what a fluid is. So these things are moving around and they collide. So what I'm going to do is I'm going to write down an equation for the collisions of all these particles. And then scattering. I can write down Feynman diagrams that describe what happens when these things come in and collide and do stuff like this. So all sorts of interesting things like that. I can write this down in various approximations, such as the Boltzmann equation, pages and pages of algebra, systematic derivations using Boltzmann equation, Feynman diagrams, all sorts of things like that. And then if I take this equation that tells you how the particles move, then I coarse grain it, then I can also derive the Navier-Stokes equations. Okay, so then I can do this. So I can get equations for the correlation functions. And I can coarse grain. And I can get equations for the local velocity. So I can kind of claim that I do this, but actually I can't because this is a strong coupling problem. So in actual fact, we do these calculations perturbatively. In the strength of interactions between the particles. Kind of like we did for the Gross-Putievsky equation, and then if I do this correctly, then I get the Navier-Stokes equations. But I also get something else. I get the Navier-Stokes equations. I also get a formula for the shear viscosity. Okay. So that's the other way that I can do that. Okay. All right, which way is better? Okay, obviously the second way I didn't describe it, I didn't do it for you in detail because it would have taken me probably 2 or 3 lectures to derive it and do all the calculations. But you sort of roughly get the idea of what I would have done. Okay, so the question is, which way is better? The second way. EJ is saying it's the second way. Yeah, much better. It must be right? It must be better because it's got Feynman diagrams in it and things like this, right? Okay, so who agrees with EJ? I'll say, who would agree with EJ if they didn't think that I was going to try to trick them? Okay, nobody wants to agree with EJ. Okay, who doesn't agree with EJ then? I know you two don't, so I know you know why. Well, what about the rest of you? What do you think? So you've got a choice between a very systematic, detailed calculation, which takes 3 lectures to do, and like 30 seconds of hand waving and waffly BS. And which one do you think is better?
I think it's necessary to like do a very detailed like particle by particle.
So you think the second one is you don't need to do it. You think it's too detailed. That's an unusual comment in a class in theoretical physics. But yeah, okay. So what do you think, Chen?
I would think like the second one is necessary, but like to verify the first one.
Okay. So Chan thinks that you don't need to do the second one, but you could do it if you wanted to verify the first one. Again, that's kind of along the lines of what you were saying. That's reasonable. Anybody else want to say anything else? Okay. So the answer is, which one is better? It's by far the first one. Okay, by far. Okay. So, all right. So, Srijit, why is the first one better?
So first one is just economical.
The first one, what?
It's very economical.
Okay, well, okay. Okay, well, the shareholders of the company that makes pencils might disagree with you that it's more economical.
Well, at least a physicist, the grad student doing that calculation would agree with me.
Okay, so basically, you think it's better by the principle of least action. you have to do less work.
That's one. I think the second one also you have to assume a lot. You have to assume that there's not a lot of interaction between all the particles. You're taking, I think, quantitative directions to it. So
right. Okay, you can stop that. Okay, so that's the point. Okay, so the point is this: the first argument, the 5 minutes of hand waving and waffly BS, that's called phenomenology. Okay, well, I use symmetry principles and general arguments. So phenomenology is symmetry plus conservation laws plus constitutive relations. In this case, the idea that you have a linear shear viscosity. So that's what's called phenomenology. So that is definitely much better than the microscopic derivation. And the reason it's better is, as Srijit said, it is because it has a greater degree of generality. So the microscopic derivation is only valid at, for example, low densities. I'm expanding about an ideal gas. So I'm doing kinetic theory. I'm doing Boltzmann's equations, and I'm trying to take into account the scattering in a as detailed a statistical way as I can do. But it is still an expansion about an ideal gas, and so it does produce something that the phenomenological one doesn't produce. It tells you that in terms of microscopic parameters, but the point is that the Navier-Stokes equation is valid for dense fluids. So like a liquid, okay? So the Boltzmann equation approach is not valid for that. So the price you pay for being able to calculate these parameters is that you're doing it in a regime where you can do perturbation theory. But I don't care about what the number is. I want to know what are the phenomena that happens once I've got the equation. So I'm quite happy to say, okay, the viscosity is whatever it is. We'll just put it into the equation. We'll get it from experiment. Comes from a lower level of description, but we don't need to know about it because actually we don't care about the atoms. We care about the patterns at large scales. So we're not interested in the actual, how does the shear viscosity depend upon the mean free path and and so on and so forth. So this is valid for dent. I'm going to write this word again, because it's important. The dense fluids, and so it has a greater regime of validity. So remember, keep your eye on the ball. And the ball in this case is we want to understand the long wavelength description of the system. Of the patterns and not the particle collisions. So we hope that there is this scale separation. And in another paper I wrote, this comment became quite famous in some, or infamous in some sense. The comment was, don't model bulldozers with quarks. A bulldozer is a machine that you use to build roads and buildings and things like that, and quarks are quarks. Okay, so choose the right level of description. Okay, so let's go. So that's part of the equations. So we're not done yet. Okay, we still have to talk about heat transport. So let's talk about heat transport. Well, that's easy because we know that temperature diffuses. So we have heat diffusion. So we just say that T by dt is equal to some thermal conductivity times del squared T, and this describes a diffusion. But remember that diffusion, this is a scalar quantity, like this quantity F over here on the left-hand side, and that is transported. So there's also another term, which is, let me write it like this. That goes in here. So this is advection. And then this one over here is just a diffusion. So this is sometimes called a passive scalar advection. I have a scalar temperature that is advected with a fluid, except it's not really passive, because here's the problem. Is it really passive? Not really. Why? And the reason is this. In the Navier-Stokes equations, which we have over here somewhere, notice that in the Navier-Stokes equations, we have also the density. And that density depends on temperature. So it would be, so passive would be U determines T, and then that's the end of it. But active is the following. U determines T, and then T determines U. Okay, and that's what we have here. And this little bit happens because rho is equal to rho of T, and rho of T goes into the Navier-Stokes equations. Okay, so that's a complication that we're going to need to worry about, and basically what we'll end up doing is essentially throwing it away in some sense. Okay, so that's the heat equation. All right. So the next thing we want to do is now we've got the governing equations. We know that the fluid goes into motion. So, but it only goes into motion when you heat it by enough. So now what we're going to do is the following. We're going to ask when is the fluid stationary? So we're going to work out an equation for that. And then what we're going to do is we're then going to ask when does it start moving? So what we're going to see is that we can construct a steady state of the system. And it's quite easy to do, and we'll do it quite quickly. And then once we've got the steady state, then we will ask ourselves the question, is that steady state actually stable? And we're going to see that it's not stable. So what we're going to see is that there exists a steady state. And this can become unstable in a technical way, which we'll define for large enough delta T. And in fact, we're going to construct a control parameter, which will not just be delta T, it'll be a whole ratio of all of the quantities in a certain way. And when we've done that and we'll derive it, you'll look at it and we'll say, all the things that we thought should be helping the fluid motion, they help it. And all the things that we thought should act against it, they act against it. And we'll see that explicitly in the way that we construct our control parameter. Okay, so now let's go and do an honest calculation. So I'm going to go through this as economically as I can. So let's start off with a steady state. So for the steady state, what we want then is U is equal to 0. So that's going to be a uniform state. So then let's go back and at the diffusion equation. So then the diffusion equation is going to look like this. Kappa d2t by dz squared is equal to 0. So again, I want you to remember, here's our geometry. So our geometry, if there's no pattern, everything is going to depend on z, but it won't depend on x and y. So there is a z dependence because we have a temperature gradient. So we definitely have to solve this equation, and this is a simple equation. So so the solution to this is t is equal to t of z, which is t naught Nope, I'll call it TL. Minus Z over D times delta T. So delta T is the, I wonder why I got a minus sign there. Oh yeah, that's perfectly correct. Yeah, yeah. The temperature at the top is lower than the temperature at the bottom by an amount delta T. Okay, so this is the temperature at the lower boundary. So then, so now that I know that the temperature goes linearly, what that means is that I compute the density. The density is a function of temperature, but temperature is a function of Z. So that is rho of Z. And that I could write as some rho bar times 1 minus alpha T naught of Z minus T bar, like so. So this T here, this T here I'm going to call T0. Okay, so that's how the density varies. It varies linearly with Z as well. Then what is the hydrostatic pressure? So so I know that U is equal to 0. So U is equal to 0. So that means that minus dP naught by dz minus rho naught of Z times G is equal to 0, just plugging in from the Navier-Stokes equation. And so that gives me how P depends on Z. So I just have to solve that equation. And I know that rho is linear in Z, so I can just solve that equation for the pressure. Okay, so that's the steady state solution. Okay, so now I want to look at the instability of the solution. So this is section 3 in my notes, the instability of this uniform state. So the way I'm going to do this section is I'm going to start doing the calculation, and then halfway through, we're going to see that we've got a mathematical problem that looks really nasty. So then I'm going to step back and say, let's think of this in some more abstract form. I'm going to show you what happens in an abstract form. And then once we've done that, we're going to go back to the actual equations that we want to solve. So here is our goal. We're going to say that I know that T is equal to T naught of Z. That's my steady state. I know that the pressure is equal to P naught of Z. I know that U is equal to 0, and I know that rho is equal to rho naught of Z. So those are the steady states. And then what I'm going to do is I'm going to add to these terms a T1, a P1, a U1, and a rho 1. And what I'm going to try to find out is what is this? So these are the perturbations. Around these steady states. And then the question that we want to understand is, what is the equation of motion for the perturbations? And we're going to do this equation of motion for the perturbations to lowest order in the perturbations. Okay, so we can get a very complicated equation, but that doesn't help us. So our hope is that by linearizing, we can understand what happens. And the real question is, once we've got that equation of motion, do these perturbations die away? And that means we get back the stationary state. Or do they grow? And then the question we can ask is, if they grow, then into what? What happens next? And let's talk about the premise of this type of analysis. Let's talk about this in statistical mechanics. So we've already done something like this, this kind of picture already in statistical mechanics. So there's an analogy to phase transitions. So let's talk about that. So let's suppose that I have a system like a magnet or something like that, where I draw the potential for the order parameter psi, and we know that what that potential looks like is above Tc, the potential for the order parameter looks like this, and then if I go below Tc, the potential looks something like that, and you get spontaneous symmetry breaking. And now we know, of course, in a bit more detailed, sophisticated way, what we really mean when we talk about this. So here I've just drawn that V of psi is 1/2 a psi squared plus b over 4 psi to the fourth, and so you might say, well, let's suppose I compute the the particle sitting at the origin. Okay, so there it is in a stable situation for t greater than Tc. Now, what happens when t is less than Tc? So when so this is stable for t greater than Tc, but for t less than Tc, it's unstable. And we know that it's unstable because we can measure the restoring force for t greater than Tc. That is positive. And the restoring force for t less than Tc is negative. And you can see that because if I displace this particle, so let's suppose I were to displace this particle to this point over here, it would experience a restoring force above Tc and move back to the origin. But if I'm below Tc, what it's going to do is it's going to just fall down this potential well like that. So for t less than Tc, the particle moves away from the origin. Now, so all we want to know for now is this: does it move away? Or return? That's the linear stability question that we're asking on the left-hand side. Now, the next question, the final question is, what is it unstable to? And we know in statistical mechanics what the answer is. What happens is that as time goes to infinity, the system for t less than tc ends up at either this minimum or this one. So it's going to end up with psi is equal to minus a t over b square root plus or minus. Okay. So what I want you to notice about this formula, and this is an important point, is that the order parameter is restabilized at a value that depends on b. And what is b? Well, b is the coefficient of the psi to the fourth term, which controls the nonlinearities. So it's restabilized a value that depends on b, i.e. it's restabilized by nonlinearities. So that's what happens in statistical mechanics. It's restabilized, and what that means is that it becomes stable, but in a new state. The new state is the state of spontaneously broken symmetry in the case of equilibrium statistical mechanics, but it's something completely different in the case of a non-equilibrium system. Okay. So, by the way, this is for the benefit of you. This nonlinearity that stabilizes it here, this nonlinearity that stabilizes it is an example of a dangerous irrelevant variable. Okay, so why do I say that? This is really for Chan's benefit because it's of research from that we're working on, not for anybody else, but I'm just going to mention this. If you're above the critical dimension, okay, you might think that, well, mean field theory works, so why do I need to worry about the nonlinearities? So for d greater than 4, I don't need to worry about it. The nonlinearities are irrelevant operators, but they cannot be removed because they are still important at determining the restabilization of the system below TC. So even though a variable is irrelevant in the renormalization group sense, it still matters for the statistical mechanics. And what that means is that if you're above 4 dimensions, it messes with all the scaling laws, and that's particularly the scaling laws to do with hyperscaling. Okay, and so why do I mention this? Because it matters when you do finite size scaling. Okay, all right. So this is a very, very subtle point, and if you want to know more about those things, you can look in my book, Search for Dangerous Irrelevant Variables. But we don't need that here. Okay, so let's go ahead and work out the equation of motion. So we've got 4 variables that we want to find the equations of motion for, T1, rho 1, U1, and rho 1. So let me go and just simply write down what those equations of motion are. You can do the linearization yourself. So let me write them down. So rho 1 rho 1 is minus alpha rho, the reference density rho bar times T1. Divergence of U1 is equal to 0. Rho naught of Z d U1 by dt is equal to minus grad P1 plus eta del squared U1 plus rho 1 times G, and d by dt of T1 plus W1 dt naught by dz is equal to kappa del squared T1. Okay, so those are the four equations of motion. And here, let me just say what I mean by this. So here I've written that U, the vector U1 is equal to U1 V1 W1. Okay, so the components of the velocity in the x, y, and z directions are U1, V1, and W1. So this is the equations that you get. So all the quantities with 0 are the stationary quantities. All the quantities with 1 are the dynamical ones that we want to solve. Okay, so now we have to solve these equations. So now let's step back and discuss again what we expect to get out of this. So now let's discuss what we hope to calculate in general. So I would say that what we have here is, and this is an example of, I've got an equation of motion for some field that depends on x and t. Psi might be multi-component, it doesn't really matter. It has some nonlinear function of psi x and t, so that's the equation of motion that we want. That's n is some nonlinear operator. We have a steady state, which we'll call d psi d by dt of psi naught is equal to 0, and so that means that this nonlinear operator of psi naught of x and t equals 0. So that's the equation that determines our steady states. Then what we do is we write down perturbations. So we write that psi naught is psi naught plus psi 1. And then what that means is that the equation of motion for psi 1 is equal to d psi 1 by dt plus n psi naught plus psi 1 is equal to 0. But we want to linearize this. So what we end up with is d psi by dt, d psi 1 by dt plus, I'm going to write this, it's a Frechet derivative, but I'll write it sort of like this, dn by d psi evaluated at psi naught of x. That's some operator acting on psi 1 of x and t is equal to 0. So that's what our equation of motion is. And this operator dn by d psi is the linearized version of the operator evaluated about the stationary solution. And then there are terms that we've neglected, which of course are order psi 1 squared. And we're going to throw those things away. So what we have here is by construction, we've created a linear stability problem. So I can think of this as being of the form d psi 1 by dt is equal to L, some operator, times psi 1 acting on x and t. And this operator L is the operator dn by d psi evaluated at psi naught of x. Okay, so this is a linear stability problem, and so now I want to know, well, what's going to happen if I make a perturbation? So the question that we ask is this: let us make a perturbation where we write psi 1 of x and t is equal to some amplitude e to the I k dot x plus omega t. So we're making a perturbation, we're doing a Fourier analysis, but the different modes may grow at different rates. And so we have to allow for the possibility that omega is a function of k. And we're going to find out what function that is. So if we plug that into our linear stability analysis, then that means that we get omega of k psi 1 is equal to L psi 1. So what we have here is that the frequencies omega of k now are given by an eigenvalue problem. So omega of k, that is a thing that we call the dispersion relation. And this is an eigenvalue of the operator M. Okay, so you say, well, that's great. I know everything about eigenvalues because I've taken graduate quantum mechanics out the wazoo, so I know how to solve these problems, but not so fast, because note that L is in general not a Hermitian operator. And in fact, it may have very, very different mathematical properties than what you would have come to expect from quantum mechanics. So omega is the dispersion relation, but what is the physical significance of omega? So omega of k is the growth rate of a perturbation with wave number k. Okay, so what can happen? Okay, so we obviously have to calculate this, and we obviously have to provide some boundary conditions and so on and so forth. But what are the possible outcomes of such a calculation? So let's try to enumerate them. So let's suppose, for example, so here's outcome number one. What we may have is that the real part of omega of k is negative for all k. So any Fourier component will have a real part that is negative. It may have an imaginary part, in which case there'll be oscillations, but its real part is negative. So that means because it's going as e to the plus omega t, the way I define it, what that means is that the real part of omega is negative, then that means that any Fourier component will exponentially decay in amplitude. And so what that means then is that if that happens, then we would say that the state that we're expanding about, psi naught of x, we would say is stable. Okay, except it's not really stable. We only know it's stable to linear analysis, so we have to say that it is linearly stable. Okay, there might be nonlinear effects that make it unstable, but at least we know that it's stable at least linearly. So that's the first possible outcome that we could get. The next outcome that we might get is, well, you could say, well, okay, so something like that doesn't happen. Let's suppose that the real part of omega of k is positive, and may not be positive for all wave numbers. So let's say it's positive in a band. Let's say k1 is less than k is less than k2. Okay, so that could be one of the situations that happens. So in this particular case, then the Fourier components in this band will grow exponentially. And so what that means then is that the amplitude of these modes will increase. And you might say, so then what's going to happen is it's just going to grow and diverge, and it's going to be unstable. But that's not true, because remember, all we're doing is linear stability analysis. So all we can say is that up to linear stability analysis, it's going to grow into a regime which is outside of the regime of validity of linear stability analysis. It's not, again, it's not a self-consistent calculation. Once it becomes positive, then once the real part becomes positive, then it's going to grow and then eventually violate the self-consistency that we talked about last time. So what we can say is the amplitude will increase and become non-infinitesimal, and that means it will grow out of the regime of validity of linear stability analysis. Once it grows out of the regime of linear stability analysis, that means that neglecting the order psi squared terms is not justified. And remember what we talked about a few minutes ago. A few minutes ago, we talked about this picture of the analogy with phase transitions. What we saw there was that the nonlinearities restabilize the system. So what may actually happen here is that the neglect may not be justified, and that means that the nonlinearities may, but they don't have to, restabilize the system. So what we would say is that the state psi naught of x, what we would say is that the state psi naught of x is unstable. But that's not really true. Well, it is unstable, but the way we would have to say it correctly is that it is linearly unstable. And it may be linearly, non-linearly restabilized into something else later on. So the drawback of linear stability analysis is that in linear stability analysis, we cannot say what it restabilizes into. We cannot say into what state it restabilizes. So we have to do a more complicated calculation. And then there's another case that can happen. In fact, there's lots of cases when you start to think about it. So what you might have is that the real part of omega of k is actually less than or equal to 0. And that means that you have marginal states and those states, why are they called marginal? Well, then the real part of omega is equal to 0. And if the real part of omega is equal to 0, then your perturbation doesn't behave exponentially. So then you need to go to higher orders. So then you have algebraic behavior. So once that happens, then you need to do a higher order analysis. And of course, I'm not going to go into that. So this is the general picture, but it's not like this thing has to happen all the time. This happens depending on what are the parameters in the problem. So we have in our problem particular control parameters. We have the thermal expansivity. We have the baseline density. We have the thermal conductivity, the viscosity, thermal conductivity, and so on. Okay, so in reality, when we write down our equation of motion, d psi by dt is n, some nonlinear operator acting on psi, actually there's going to be some control parameter in here that we call epsilon, that we talked about last time. And so in reality, what's going to happen is that the behavior depends on epsilon. So let's have a look and see how it depends on epsilon. So let's have a look, first of all, in scenario 1. So here what I'm going to draw is I'm going to plot k along here, and here I'm going to plot omega of k. And when I write omega of k, what I really mean is the real part of omega of k. Okay, so that's what I'm saying, but I'm just going to write it as omega of k. So what we've seen then is that if epsilon is less than some critical value, then I might get something like this. So that would be one scenario where everything is perfectly stable. Then I may have another situation where, actually I can probably draw it on the same graph. I can draw it where now what happens is this thing goes like that, and then this is epsilon equals epsilon c, and this here is some critical wave number kc, like so. And then at higher values of epsilon, I might have a situation like this. And now what's going to happen is I have a band of unstable wave vectors. So that's the region over there. And so in that band, it's unstable. And then over here, it is stable. And over here, it is stable. So that's the situation when epsilon is above the threshold. And so the phase diagram is that you're stable in a linear sense for epsilon less than epsilon c, and unstable when epsilon is greater than epsilon c. So that's what we've just described. And then the behavior in this unstable regime is going to be very complex. And there's no two ways around it. So there are some simplifications that one can make. So what are the simplifications that one can make? Well, first of all, it might be that the size of these modes, so let's call this K1 and this one K2. So it may be that the size of this band of unstable wave vectors is much smaller than the critical one Kc. So in that case, what it basically means is that we can essentially say that there's only one or two unstable modes. And those modes will presumably restabilize. We'll have to see if they do or not, but let's suppose that they do. They might restabilize into a pattern. And what we would expect that the fastest growing mode will give you the scale of the pattern. So for example, here we have the fastest growing mode. That's the one I'm drawing over here. So then that would be K max. And then the fastest growing mode would be omega of K max. And so then what we would expect that we get the physical picture in space looks something like this. Here is my order parameter. It's now some periodic pattern like that. And this is the wavelength for lambda, and lambda would be given by 2 pi over k max, where omega k max is the fastest mode. So that is indeed one of the few things that we can extract from linear stability analysis. And to do any better is really hard. So what I've just explained to you is this is the basis of virtually everything we know about pattern formation. So this being linear stability. So to do any better, you can say, well, once I'm in the unstable regime, what can we do? And the answer is two things. So answer number one is we can do weakly nonlinear analysis. So we can actually take into account the nonlinearities. I'm going to show you a dirty trick to do that by renormalization group. So you can do that. So that's answer number one. And that will only be true for epsilon just slightly greater than epsilon c. Okay. But there's another thing you can do. Answer number two is that you can look at phase modes. And this might be true for epsilon much greater than epsilon c. And I'm not really going to go into that in this course. We don't have enough time. But this is the analog of what we did in the first part of this quarter, when we looked at statistical mechanical systems which exhibit emergent behavior, and we looked well below TC. When we looked well below TC, we saw that the amplitude modes got frozen, and then we just looked at the phase modes, and then we looked at the dynamics of the phase modes. And from that, we were able to look at the dynamics of topological defects and so on and so forth. So you can do the same thing here as well. So you can look at phase modes. And so this is the analog of looking at continuous symmetries for temperatures much less than TC. Okay. So that's the general picture. All right, so I want to spend now 5 minutes telling you the results of what will happen when we apply this to our convection equations. So for convection, we have 4 coupled differential equations. So it's a bit of a mess, okay? So I'm going to show you, I don't think what I'm going to do is I'm going to go through every single step of the calculation. I'm just going to show you, roughly what happens, and you can, if you're interested, you can go and look in the detailed notes. So the next thing we're going to look at now is in ESM 7.3.1 and 2. We're going to look in here. We're going to now look at the linear stability analysis. for our convection equations. So you're not going to follow the algebra in real time. So don't worry about that. Let me show you how it works, okay? So the main thing that I want you to remember is that we have our system set up like this. This is the spacing D. Gravity is going down like this. This direction is Y. This is X, and this is Z, and this is hot, and this is cold. Okay, so that's our geometry, and what we care about is the velocity field in the Z direction. That was the equation that we had in our system. So over here, let me show you the equations. So over here, look at this term. So there's a W1. So we're going to go and solve for that one first. Okay, and you'll see why in a minute. What our strategy is going to be is to try to work out what happens when we look at this top down, and I'll show you how we do that. So step one is solve for W1 of X, Y, Z, and T. So how do we do that? Well, I'm going to write that W1 of X and T is equal to some function in the Z direction, and then some function in the X and Y direction, and then e to the omega t. I'm going to basically do separation of variables, just like you would expect. So then plug that in, and what you're going to find is that the equation of motion for these terms are following: dx squared plus dy squared f of x, y is equal to minus a squared f, and this a is going to be some eigenvalue. So we're plugging this into our Navier-Stokes equation. I'm going to use the notation, write down d. That's the operator d by dz, and I'm going to write another operator. Actually, I'm going to show it to you. No, I'll just leave it like that. So d is d by dz. If you plug that in to the equations, what you end up with is this: nu d squared minus a squared minus omega I'm going to go and check that the equation I have there is correct. Give me 1 second here while I pull up my more detailed notes. Okay, so yeah, this equation isn't correct. Okay, so this is the equation that I get for W. Okay, so it's a linear equation. It has 2, 4, 6 spatial derivatives in it, and we have some boundary conditions. And what are the boundary conditions? Well, let's write those out. And actually, I think what I'm going to do is I'm going to give you the boundary conditions on Thursday, okay? Because I'll write them down and then we're going to solve it. There's no point in me trying to do that right now. So, so on Thursday I'll start off with the boundary conditions. So, if you want to know how I derive this equation, you can look in section 7.3.1. It's one page. Okay. If you could do that, it would be great. If you can't do it, I can go over it again next lecture. But it just quickly goes through how it was that I was able to beat down those complicated 4 simultaneous differential equations into one differential equation for one variable. Okay, so that's the trick. And the price you have to pay for that is that the equation for one variable is a 6th order differential equation, whereas before I had 4 equations which were only 2nd order. Okay, and only 3 of them, one of them was an algebraic equation and the other 3 had derivatives. So I turned 3 2nd order equations into one 6th order equation. Conservation of difficulty, 3 times 2 equals 6. Okay, all right, so we'll pick this up again on Thursday. Any questions?